Good day, uni students. I'm Norman Wildberger from the University of New South Wales, and this video and the few following it are going to give you an overview of mathematical terminology, notation, and conventions, which are ideally suited for incoming university students. I teach at the University of New South Wales. Here's my official address. I'm in the School of Mathematics and Statistics in the Faculty of Science, UNSW, Australia. This is the #1 School of Mathematics and Statistics in Australia, and probably the #1 school in the Southern Hemisphere. It's a great place, and we have students coming from all over the world to learn engineering, arts, science, law, etc., etc. So if you are a student who's coming from overseas, from a non-English speaking background, naturally you are going to be perhaps at a little bit of a disadvantage when it comes to the terminology used in mathematics. Because mathematics is, of course, a highly technical subject where we use words in a very precise way. So these videos are meant to give you an overview of terminology that I expect you to know when you're coming into first-year mathematics at the University of New South Wales, be it for engineering, finance and actuarial studies, science, or perhaps in conjunction with law or medicine. So we're going to go over various topics, and I'm going to quickly summarize the essential terminology. So let me just point out, for reference sake, where University of New South Wales is, and in particular where my office is. So here is the big block on which the University of New South Wales is located. It's in Sydney, in the eastern suburbs, and it has Anzac Parade, which is the main street fronting the main entrance. There's also High Street and Botany Street and Barker Street making up a big rectangular area. In terms of orientation, this is north in this direction. The Pacific Ocean is east in this direction, probably about 40 minutes walk. The city downtown is in this direction, about a 20-minute bus ride. And about a 10 or 15-minute bus ride in this direction, you get to La Perouse and Botany Bay. So here along the main walkway into the campus on the right-hand side, just after you go past the playing field, is the Red Center, which is the home of the School of Mathematics and Statistics. And I'm in the East Wing, and my office is RC 4108, and you can drop by anytime and say hello if you like. And my email is n.wildberger@unsw.edu.au, but you can also ask questions or leave comments with these videos. All right, so welcome to the UNSW. For those students who are coming here for the first time, you're going to have a great experience. You're going to learn a lot of things, and it's especially important to do well at mathematics, which is a core subject for all technical areas. And in order to do well in mathematics, you have to understand what the words mean and how the notation is used. So let's start today with numbers and arithmetic. So a good place to begin is with the natural numbers or counting numbers. The numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So the symbol that we use for the natural numbers is often this bold N. Then we can extend the natural numbers to include 0, as well as the negative numbers, -1, -2, -3, and so on. And that gives us the realm of integers, usually denoted with this Z, again with a sort of bold bar there. The next numbers that one learns about in primary school are fractions, or rational numbers. Things like 3/4, or 3/4. And sometimes we use this symbol with a slanted bar, but probably more likely you're going to see 3/4 written this way. It's especially true when the numbers are bigger. For example, here, -192 over 3,451. That's a fraction. And our quick symbol for the rational numbers is this bold Q. In engineering applications and science, floating point or decimal numbers are very important. So here is the number 78.94. That's the decimal point there. And in scientific notation, this would be written as 7.894 times 10 to the 1. This is sort of the number system that computers like to work with. And then there are the real numbers, so-called real numbers, which I have to admit I'm not a big fan of, but let's not discuss that too much here. They're denoted by a bold R, and the probably most familiar example is pi, which is roughly 3.1415926, and it has a decimal expansion that goes on forever in some fashion or another. So these are 5 important types of numbers or number systems that we encounter. The natural numbers, the integers, the rational numbers, floating point numbers or decimal numbers, and real numbers. Let's say a little bit about our numerical system, which is the Hindu-Arabic numerical system, which is based on powers of 10. Here, for example, is the number 5,413.892. And this decimal point here separates the standard part of the number, which has the ones column there, tens column there, hundreds column there, thousands column there, and so on, from the decimal part of the number, which involves the 1/10ths column there, the 100ths column there, the 1,000ths column there, and we could carry on in both directions. So the numbers that are appearing here are always between 0 and 9, and they are called the digits of the number. So we would say that this number has tens digit equal to 1, has hundreds digit equal to 4. We would say that this 9 is the 100th digit of that number. So powers of 10 are crucial for the Hindu-Arabic system. It's important to understand and appreciate the terminology used to describe powers of 10. So let's review that. We start with 1, which is 10 to the 0. Then 10, which is 10 to the 1. Then 100, which is 10 squared. And then multiplying by 10 each time, we get 1,000, and then 10,000, 100,000, million, then 10 million, 100 million, and then billion, then 10 billion, 100 billion, trillion, and we could carry on. Now it's important to realize that we're going up by 1,000 when we go from 1,000 to a million, and we're going up by a factor of 1,000 to go from a million to a billion, and also a factor of 1,000 to go from a billion to a trillion. Here is a big number, and we organize our notation so that there's commas separating groups of 3. Here's the ones position, the tens, the hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, then billions, 10 billions, 100 billions, trillions, 10 trillions, 100 trillions. And when we read such a number, we read it in terms of these groups of 3. So this is sort of the ones group, this is the thousands group, this is the millions group, the billions group, the trillions group. And each of these 3-digit numbers is a number that's expressible in terms of hundreds, tens, and ones. So the way we would read this is from left to right. 495 trillion, 367 billion, 413 million, 840,000, and 59. That's how we express the, that's how we would read this in Hindu-Arabic system in English. Of course, arithmetic is not just about numbers, it's also about operations, ways of combining numbers to get new numbers. And there are 4 basic arithmetical operations: addition, multiplication, subtraction, and division. And they each have their standard symbol, although division has kind of 2 different symbols that are used to describe it. We also have these words which refer to the outcome of performing an operation. The sum for addition, the product for multiplication, the difference for subtraction, and the quotient for division. That's a bit of a tricky word, quotient. So for example, for addition, here this equation would read 3 plus 4 equals 7. This is an example of addition. And notice that I say the addition by using this word plus. So when you're actually performing the operation, you say plus. So you read this as 3 plus 4 equals 7. This sign here, of course, is the equality sign, so telling us that what's on the left-hand side and the right-hand side are the same. That's sameness in mathematics. Equality, we call this the equals sign. In this example for multiplication, 5 times 12 equals 60. So we use the word times. For subtraction, 12 minus 15 equals negative 3. Okay, so we're using the word minus there for the operation of subtracting. And here, for division, 26 divided by 2. And sometimes we say 26 over 2. Means the same thing. So 26 divided by 2 is 13, or 26 over 2 is 13. We especially use that when we have one number on top of the other number with a bar like this. Generally speaking, at the university level, we prefer to use this notation for division. Okay? So we want to let go of this to a certain extent. This is sort of a high school, primary school kind of notation. This is better suited for algebraic work. Now these operations satisfy certain laws or rules. And these are 3 important words that describe some of these important rules. The commutative law says that 3 plus 4 equals 4 plus 3. It doesn't matter if you interchange the order of an addition, the result is the same. And there's also a commutative law for multiplication. 5 times 2 is the same as 2 times 5. The associative law for addition is like this. 6 plus 2 plus 3 equals 6 plus 2 plus 3. We can only combine 2 things at once. Here we're combining the 6 and the 2 first, and then adding 3. Over here we're taking 6 plus the sum of 2 plus 3. The associative law says that those 2 are going to be the same. And there's an associative law for multiplication too. 4 times 5 times 2 equals 4 times 5 times 2. And these symbols that we're using here are called brackets. They're used to organize the terms in an arithmetical equation. The distributive law combines multiplication and addition. So 4 times 3 plus 2 equals 4 times 3 plus 4 times 2. Or the other way around, 5 plus 6 times 3 equals 5 times 3 plus 6 times 3. So please remember these 3 important words for the laws of arithmetic. Let's say a few words about fractions or rational numbers. And the symbol for a fraction is Q, or I like to use the symbol RAT for the type of number we're talking about. So here's an example of a rational number. And this number can be stated in a number of different ways. One way is 3 divided by 4, when we think of it as representing a division. Another way, when we think of it more as a fraction, we say 3 over 4. Another way is 3/4. They all mean more or less the same thing. We usually don't distinguish too much between a division and the resulting fraction, which is the result of that division. Very important to remember that the top number is called the numerator, while the bottom number is the denominator. All right, so numerator on top, denominator on the bottom. There are some simple fractions which are especially important, that come up a lot. So this number is 1/2. This is 1/3. This is 1/4. 1/5. 1/6. And here you see the pattern. There's a 6 and then a TH afterwards. That's the general pattern. So the next one would be 1/7, and then 1/8, 1/9 to 1/10, and so on. If we have a bigger fraction, perhaps like this one, we would read this as 37 over 64. That's a simple way of saying it. This is a more complicated way of saying it, 37/64. Okay, but I suggest to you that you stick with this. This is 37 over 64. There are some numbers, some natural numbers, that play a special role in mathematics. They come up a lot. They have a special name. The square numbers are sometimes also called just the squares. And they are what you get when you take a natural number and multiply it by itself. That's called squaring a number. So 1 squared means 1 times 1, which is 1. 2 squared, that's 2 times 2, which is 4. 3 squared is 9, 4 squared is 16, 5 squared equals 25. So we call these numbers the squares. They play an important role in mathematics. A little bit less important, but also reasonably interesting and important, are the cubes, where we take a number and we raise it to the 3rd power. So 1 cubed is 1, 2 cubed equals 8, 3 cubed equals 27, 4 cubed equals 64, and so on. So here 4 cubed means 4 times 4 times 4. And then we have the prime numbers, or just the primes. These are the very interesting and somewhat mysterious pattern of numbers, starting with 2, and then 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, and so on. These are the numbers that don't have any other factors other than 1 and themselves. 1 is not considered a prime number. We'll also mention powers. It's another arithmetical operation that's very important. When we raise a number to a power, just as we're doing here, then this 2 to the 10 means 2 times 2 times 2 times 2, altogether 10 times. And I hope you know that that's 1024. This number down here is called the base. This number up here is called the exponent, or sometimes the index. And the whole number is called a power of 2. That's called a power. A 10th power in this case. Let's review a bit of terminology having to do with multiples and factors and divisibility. If we have the equation 2 times 3 equals 6, then we say that 2 and 3 are factors of 6. Or we can say that 6 is a multiple of 2, and that it's also a multiple of 3. So the multiples of 2 are 2, 4, 6, 8, and so on. The multiples of 3 are 3, 6, 9, 12, and so on. We can also say that 2 divides 6. And another way of expressing that more compactly is this notation here. 2 with a long vertical bar followed by 6 means 2 divides 6. So there's some number that when you multiply by 2, you get 6. Closely related to this is the idea of a factorization. So here is a factorization of the number 60. We're writing it as 5 times 2 times 6. We've factored this number in some fashion. We've written it as a product of other numbers. A very important kind of factorization is the prime factorization, where each of the numbers involved is a prime. So here 60 is 2 squared times 3 times 5. 2, 3, and 5 are all prime numbers. And I remind you about this fundamental theorem of arithmetic. All right, so this is a very important fact that goes back to the ancient Greeks, that every natural number n bigger than or equal to 2 has a unique prime factorization. In other words, we can do exactly what we did with 60. We can write it as a product of prime numbers, and that factorization is unique. Unique means there's only one. It's exactly 1. This is the only way of writing 60 as a product of primes. Of course, we could rearrange the terms. We could write it as 3 times 2 times 2 times 5, but we consider that to be the same factorization. And finally, let's say a little bit about order and inequalities. So all of the number systems that we've been talking about, the natural numbers, the integers, the rational numbers, and the real numbers, are ordered. It means that we have a notion of bigger and smaller, or greater than and less than. And here's our notation for that. So this means 3 is less than 4. 3 is less than 4. Or we can also write it this way, 4 is greater than 3. These two are the same, and we say 4 is greater than 3. Here's a slight variant where we have the less than or equal sign. So 15.2 is less than or equal to 17.4. Or equivalently, or in other words, to restate it, we could say that 17.4 is greater than or equal to 15.2. But usually we read across from left to right, so this is the usual way we would write this. And let me remind you that balance between less than and greater than is equality, when two things are exactly the same. 1 plus 1 equals 2. This is an example of equality. 1 plus 1 equals 2. So I hope that's been helpful to you, just to get some basic notation with numbers and arithmetic down as a start. In our next video, we're going to talk about basic terminology and notation for geometry. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.